Hello! Today we are going to be talking about ionic bonding and their properties. Miss Ahrens is going to start us off by talking about lattice energy and how it relates to melting point.
Okay, so what is lattice energy? Lattice energy is the energy that is required to break the bonds between ionic compounds.
Okay, so let me get my pen working here. It's the energy needed to break ionic compounds.
So we have a couple different pictures here of just different ionic compounds, and you can see how their structures are going to be crystalline structures. So they're going to be tight, compact structures. And so it's going to take more energy to break those bonds. Since it takes more energy to break those bonds, the melting point of these compounds are going to be extremely high.
Right, so an element like cesium chloride, it doesn't have quite the amount of lattice energy as something like sodium chloride does. Mm-hmm. And so if you've ever put salt on a stove, like in a pan, it'll start popping all over because it doesn't want to melt because it needs so much energy to actually melt. And so melting point of ionic compounds kind of varies, but typically they're very high because of their crystalline structure. So we're going to put ionic bonds have a high melting point because of their crystalline structure. Thank you.
Yep.
Got stuck there. Crystalline structure. And this crystalline structure, the only time we're going to see lattice energy is in crystals. Okay,
Yep.
so these two are directly related. So all crystals have lattice energy.
And how I always remembered lattice energy too is, I don't know if any of you have the lattice around your garden, or it's kind of like a fence,
Right.
and how it's structured is going to be really, really tight. So that's why the melting point is so high, is because it's going to be the structure of it. So just remember it's the structure and why the melting point is high. There's our garden with our fence. It's going to take a lot of energy to get in there.
It really is. Okay, so some more ionic properties, or some other important ones, would be the idea of how soluble it is. And because of this solubility, how well it is able to conduct electricity in water. Okay, so when we put a crystal in water, it will dissolve. Well, at least most of them dissolve. And so we have a little thing, and I think I've showed you this before. So this is our salt. So we know that salt is NaCl. And as we're
going to add some there into our water.
We can get it to conduct electricity. Okay, we see the light bulb shining. And this is because of the positive and the negative ions. Okay.
That form when they're dissolved.
And so here's a little better view, so you can see the salt crystals. And these green circles, those are the chloride ions, and the sodium ones are the positive ion, the purple ones, excuse me. And now you have to know, even though it looks like the bond is broken, the bond didn't break because we had sodium that wanted to give away an electron, and it did. It gave it to chlorine, and that's why there's still ions. And so even though the molecules, they can separate from each other, but they're really not breaking a bond. Because when we remove the water, oops, I didn't think that was going to remove the salt. Oh, we need to evaporate it. There we go. When you evaporate it, it'll form back into a crystal. And so the bond is still there. It's just like waiting a little bit for it to come back together once the water is gone.
And we actually did this with our filtration lab.
Right.
So we got to see those crystals reform again as well.
Right.
So we could have conducted electricity if we would have had what we had with the solution.
Right, and our magnesium oxide that we created in lab on Thursday, we will be actually able to have it conduct electricity when we do our stations.
Yeah.
Okay. So hopefully that helps a little bit with that solubility, and because of that solubility, it's able to conduct electricity because of its positive and negative ions.
Just remember what solubility means too as well, where solubility is actually going to be able to dissolve in water. And then hopefully you know what conductivity is. I'm hoping there. So conductivity too is just ability to conduct electricity. So just a little bit more vocab. We talked about this vocab earlier, but just making sure you understand the vocab.
And yeah, so conductivity, I'll just put here, able to
Produce electricity?
carry
Electricity. Here's a better word.
Carry electricity. So really what's happening is when these are dissolving, you can see these little positive and negatives. We're getting little positive and negatives all over in the water. And potatoes, they are made up of starch, which has positive and negative ions. So if you stick an electrode in a potato, it would conduct electricity. So if we put some kind of electrode in here, like a little silver plate, okay, and we have a battery hooked up to it. That's a really good battery. Okay. And then we had another little silver plate, and they're not touching each other. Okay. And we had a light bulb on this side. That is a really good light bulb too. If we put power to this, these ions would pass the electricity through it. It's able to carry the charge, and then we would get the light bulb to light up. Okay? And this directly relates to the boiling point. So boiling point refers to crystals dissolving in water, and then how much it's able to change the boiling point of normal water. So I don't know, when I make my spaghetti, when I put my noodles on, it always feels like it takes forever to get your water to boil. And so if you put salt in your water, and the ions break apart into positive and negative, when you're adding the heat to it, okay, most of you don't cook it over a fire pit, but if you did, if you put salt in your water, the time that it took your water to boil would actually decrease because boiling points are lower with ionic compounds. And that's just because of these properties of the positive and negative ions, and they're bouncing off of each other, creating more friction and able to hold more energy in the water, which makes the pressure change and the water boil faster.
Yep.
Okay, the next thing, acids and bases aren't really ionic compounds, and they're not really covalent compounds. They're kind of just special. And they kind of form formulas like they're ionic.
Yeah.
So it's like the same properties of, like, if this has a charge of 3 and that has a charge of 1, they crisscross. But at the same time, they're not giving and taking electrons.
Yes.
So they have some kind of sharing properties of covalent bonding that we haven't talked about yet, but yet they kind of seem like ionic compounds. Yep. So they kind of get stuck in the middle here. So we're going to learn about these next week. And the way that you identify an acid and a base from in a formula is by
what they have in their formula.
Right.
So to look at acids are always going to have an H in the front.
Acids always have an H in the front. And you need to memorize this. This is very, very important. Acids have an H. So you see stuff like HCl, H3PO4,
can't even think of any other acids off the top of my head.
HNO3. Okay, all of these have H's in front. Okay, it doesn't matter what's behind them, but you can kind of see how they seem like ionic compounds. The phosphate with a -3, so there's 3 hydrogen. Chlorine has a -1 charge, and there's only 1. So they kind of seem like ionic compounds, but hydrogen can't give away an electron. Hydrogen only has one. So if you drew his electron dot structure,
He's going to want to share that electron because he doesn't want to give it away.
yeah, if he was to give it away from chlorine, then he wouldn't have any electrons.
Yep. And he'd be
So
very unhappy.
They have to share this electron, but there's always going to be as many hydrogens as the other negative anion needs.
Yep.
But they're sharing. So acids always have an H in front.
And then bases are going to have an OH in the back.
OH in the back. And
At the end, I guess we could say too.
bases, we should know this compound
Which
as
is going to be hydroxide, has a -1 charge. That was one of the polyatomic ions that you had to know.
bases have hydroxide. So if it has hydroxide in the end, is it always a base?
Yeah.
Yeah, it always is a base. So
Always.
all those things that you've been naming that have hydroxide in the back, they're
That's
all
a base.
all bases, every single one of them. So these are things like calcium hydroxide,
What else is there?
lithium hydroxide, sodium hydroxide.
All bases.
All these are bases. Okay, and that's the only way you can tell these two apart in the formula. Okay, and so question here, what in the world is water? Because if you have H and then there's two O's, that's the same thing as writing HOH, right?
It is a base. And you should know that already, right?
It's a base, but
Well,
it has
it's
an H
neutral.
in front.
Ooh, touche.
And there you go. It's neutral. It's neither an acid or base. It's perfectly in between these. And you can remember that because it has an H and it has an OH in the back.
Yeah.
And that's what we're going to talk about. Acids and base, when they react together, they always form water. So if you have sodium hydroxide, which is a very strong base, okay, very reactive base, and you add it to HCl, which is the strongest
acid ever.
strongest acid, we are going to get these double replace here. So we're going to get sodium and chlorine to go together. So NaCl, hope you guys have seen this one before. And then we're going to get an H and an OH, which is water, H2O.
So during neutralization reactions, we're always going to form a salt and then water.
Right, and it comes from a base
And
plus an acid.
acid.
And they always form water. So it's kind of a unique thing with that pH scale that always holds true. So just another property that is important. All right, and the last thing that we're going to do are the two types of acids. There's only two types. There are binary acids and there are oxy acids. So just by reading these, you can kind of see what we're going towards. Binary means two. So that means there's only two elements. And we know that all acids start with,
H.
hopefully you all yelled H, okay? And then there's only one more compound.
Yeah.
So that would be something like HCl or HF or H2S or H3N. Something like this. So there's just one other thing besides the hydrogen. Okay? Now, oxy acid, what do you think that has to do with?
Oxy, oxygen.
You're
Am I
good.
smart?
Yes,
Yes.
you really are.
I'm all over this.
So, hydrogen was something with oxygen in it.
Yes.
Now, it's not binary, so it has more than one other anion. And so, guess what we use here?
Polyatomic ions. That's
This-
why you had to memorize the polyatomic ions, because you're going to have to know how to name these acids, these oxy acids as well. So if you already know the polyatomic ions, naming these oxy acids are going to be so much easier for you.
That's right, because now we're going to have to name all these.
Yeah.
Yeah, that's fun. Okay, so all of these polyatomic ions that involved oxygen are going to be oxy acids.
Yep.
Okay, and so we're going to learn how to name these next week, and we're really going to dive into these acids and bases.